Hi everybody, welcome again in the third section. We will talk today about the superposition of the forces. Which forces? We have electrical forces. We have studied in the previous section the Coulomb law, which depends on the magnitude of each charge. So we multiply Q1 by Q2 if we have two charges. And this force is just between two charges. We cannot do this force for three charges together. We need to make some processes. We'll see that today. So we cannot do it like Q1 times Q2 times Q3 and so on. And depend inversely on the square of the distance between these two charges, and the constant of the proportionality is K, which is equal 9 times 10 to the 9. Superposition means we have addition of these forces. So if we have many forces, we need to add them to find the resultant force. We mean by that the superposition. We will see that now using some examples. But you need to remember also that the force is a vector quantity. A vector quantity. We need to remember what is the vector. It means and its properties and some identities that we deal with when we work on vectors. Vector quantities mean the force has a direction. Let us remember some properties of the vectors. Now for a vector A, we know that any quantity in physics has a name. So we need to name any quantity we deal with. For example, we have a force. This force acting on this object. We need to name this force by F, for example. And we need to give it magnitude and direction. But here we are defining a vector A by using an arrow on the top of this vector for A or B. We need to remember that A has components. If we are in a Cartesian coordinate system, then A has components AX in X direction, X hat or I hat if you remember, plus AY, Y hat or J hat, plus AZ, Z hat or K hat. You can use K hat or Z hat, J hat, Y hat, I hat or X hat. I used to use actually X hat, Y hat and Z hat. It's a unit vector. Its length is 1 as you remember, and its direction is in these directions. The same for B. If A equals B, that means that each component is equal to the same component in the other vector in the same direction. If we need to add two vectors to other, now we need just to add the components together and use the direction of their direction. Means A plus or minus B as vectors, it is equal to AX plus minus BX in X hat plus AY plus minus BY in Y hat and so on for the Z hat direction. Now this is just if we deal with them in their components, but we need to understand more by drawing these vectors, and we do that commonly, and it helped us to understand or solve any problem. If we have the two vectors A and B, you can see that they are both in the same direction, even if they didn't start from the same point, but they are parallel. And also B is bigger, or the magnitude of B is more than the magnitude of A, or we can say it like that, like the length of B is more than the length of A. We will see how to compute or to find the length. If we need to add them together, we just put tail to head. Okay, what's the tail? What's the head? When we draw B, for example, we start from a point, which is the tail, and end with the another point with an arrow at that point, the length of that straight vector proportional to the length of the vector or the magnitude of that vector. When we add them together, we just put the tail of B at the head of A. We have them like this. Then the resultant vector is C, which is A plus B, which is equal to B plus A if we flip them, or not flip them, actually exchange between them. And that, also A minus B means A plus minus B. If we just flip P, this means we have negative B, so it will be A plus negative B, which is A minus B. It's the same thing. We start with A. At the end of A, we start again with B, put B at the end of A, and we have it in the opposite direction, so that the resultant vector is C. And we can see that the direction of C is the direction of the bigger vector, which is, or the longer vector, which is B in this case. And in this case, if we need to find A minus B, it will be negative B minus A. It is the opposite. We cannot say it's the same as the addition. What if they have an angle between them, A and B? They are not in the same direction. The angle between them, actually, if we need to draw them, we draw A, then we draw B from the same starting point. This is the angle between them. It is not this, actually. This is the outer angle, or the complementary angle. So this angle equals 180 minus the angle between A and B. We name it theta, phi, or anything you need. So we have A, then we put B at the end of A, and this is the resultant vector, C. And the angle between A and B is this one, which is theta here, which is different than the angle of C. This is theta C, for example. It is different than this one. We can find it. Now in our solution for our examples, we have something like this, but it is easier for us if we deal with the right triangle. It has some properties, some identities, easy to be applied. We will see that in the next examples, or the next lecture examples. If we have now the angle B and the vector B and the vector A, the angle between them again is 90 degrees. Okay, which is equal by pi over 2 in radians. So the resultant vector C, as you see here, it's B plus A, or A plus B. It is the same. If we go from here to here, it is A plus B. Okay, so the length of C, we use the Pythagorean theorem, which gives us, it's the square root of the length of A squared plus the length of B squared. This is C as the length of it. So the magnitude of the resultant vector is found by this way. Okay, we are dealing with a vector. Knowing just the magnitude of that vector is not enough. We need to know the direction of that vector. The direction, it is easy to do that by finding the angle above the x-axis. For example, if this is the x direction, then C has theta direction above the x horizontal axis. This theta, we can find it by using the sine or cosine or tan theta's identities. We know that the sine is A over C, length, I'm talking about lengths. Cosine theta is B, length of B over the length of C. and the tan theta is A, length of A over divided by the length of B. After finding C, you can use any one of them when you solve the example or the problem, and they will give you the same result. We need to find theta. Theta, it may, if you solve here, it will be here theta, it will be sine inverse. If you solve here, theta will be cosine inverse. If you solve here, theta will be tan inverse to this quantity. What about the length of A? It's simply the x component squared plus the y component squared plus the z component squared if we are in 3 dimensions. But if we are in 2, just 2 components if it is x and y, or x and z, or y and z. So this is the sum of important vectors identities. We need to use them in the problems. Now, starting this, to know what we mean by superposition of the forces or vectors, just by solving examples. Let's make it directly now by solving the first example. I will not talk too much about the words here, but what we have, 2 charges, Q1 and Q2. Q1 is 6 microcoulomb, Q2 is 3 microcoulomb. Both of them are positives, and they are located on a distance which is from 0 to 15 centimeters or 0.15 meter. Okay, we need to see or to compute the resultant force on a test charge. We consider this test charge in this example equals to -2 microcoulomb. Negative. Okay, but we need to solve it in 3 positions: at position A, at position B, at position C. We put this discharge here at A and compute the resultant force, then put it at B and compute the resultant force, and put it here and compute the resultant force. It's just 3 parts or 3 examples in one. The point, the position A, it is at before that, A and B and C and the Q1, Q2 positions, all of them are located on a straight line. So they are all on one direction or one dimension. So this problem is a one-dimensional problem. Okay, it's here. Means it is easy to deal with it. It is not 2-dimensional or or 3-dimensional. We just need to deal with x component, not we need to deal with the x component of the vector, not y, not z. We can consider this as y or z, but I assume it's in the x direction. If you need to start solving the problem, you need to assume and start by considering the coordinate system. I consider this is the x axis and my origin. I need to know where is my origin. I consider or assume that my origin at Q1. Q2, it is 15 centimeters to the right of Q1. The point A, it is 20 centimeters to the right of Q1 or the origin. The point B, it's at 0.1 meter, which is 10 centimeters. And the point C is 10 centimeters to the left of Q1 or the origin. We can know easily what is the distance between each point of those A, B, and C and Q2. Okay, let us solve the problem at A position. Now, the test charge is Q, capital Q, which is negative 2 microcoulomb at point A. Let us see now what we have, or our system. We have Q1, Q2, and this is point A here. This is Q, which has a negative sign. Both of these charges are positives, so we have attraction forces between Q1 and Q, between Q2 and Q. So I name them by F1 to the left, which is to the direction of that attraction force, which is the direction of Q1, and the other force, the second force, is attraction to the left too. We have now the charge Q at point A, and there are two forces to the left in the same direction. If we have two vectors in the same direction, we need to find the resultant vector. We need just simply to add them together. So the resultant vector, the F total or resultant, equals to F1 plus F2. And its direction, we can see that it's to the negative I hat or X hat. Okay? Simply, we have this force equal to F1 and plus F2. F1, we can find it using the Coulomb law. F2, we can find it by using the Coulomb law. And this is F1, and this is F2. F1, K times Q1 times the test charge Q over R1 Q, from 1 to Q squared, plus K times Q2 times the test charge Q divided by R2Q, from here to here squared. R from here to here is 0.2 meter. R from here to here, this is at 0.15, this is at 0.2, which is 20 centimeters, this is 15 centimeters. So this distance is 5 centimeters. Okay, which is R2Q. Okay, now the second step, just put the values for each parameter or each term here. So K is 9 times 10 to the 9. Q1, it is 6 micro, which is 10 times 10 to the minus 6. Q, which is the test charge, it is negative 2 times 10 to the negative 6, plus divided by the distance, which is 0.2 squared. I use it in meters, not in centimeters, because I have to use the standard units. Plus 9 times, which is here, K, times Q2, 3 micro, times Q, which is negative 2 micro, over the distance squared. Now, the negative charge from Q, the test charge, it tells us about the direction of the force, which is attraction to the left. So I put it here just to show you I don't need it anymore. I drop it, or I don't use it because I already used it when I define or I find the direction of the forces. There is another way, but I need to use the direction or deal with F as a vector and use I hat here and here. It will be a negative sign. It's the same way of solution, but different steps. So I just show it to you here, but I will not use it. I will drop it because I already used it here to define or find the direction. So the constant K in both terms is the same. I can take it outside as a common term. And for this, it's 12 times 10 to the negative 12. And here also This time this is 6 times 10 to the negative 12, and the distance square is here, which is the first distance and the second distance. As you see here, we have 10 to the negative 12. 10 to the negative 12 is the same in two terms. I can take it outside. This is math step. I can take it as a common factor. I put it here. This is the constant from before. And these are the values for the first term and the second term. So, which is equal to, finally, 243 times 10 to the negative 1. Negative 1 means I'm dividing by 10, means I need, if I have 0 point or point, this is the decimal point, and I have 0, I need to move it to the left by 1 step, which is negative 1. So the last force magnitude is 24.3 newtons to the left, because I found that from before, if you remember. Or I can write it as a vector. F total equals to 24.3 newtons, the unit, in the negative x direction or negative I direction. This is for the first part of this example. What if we need to compute this at point B here? So we have Q1, which has the same charge magnitude. We have Q2 too. Okay, this is Q2. Remember that Q1 is 6 micro, Q2 is 3 micro, and the test charge is negative 2 micro. The test charge now at point B, which is 10 centimeters from the origin and 5 centimeters to the left of Q2. It is negative, and these charges are positive. So we have attractive forces between the test charge and the both of these charges. So the first force is between the test charge and Q1 to the left. The second force between the test charge and Q2 to the right. So we have two forces with opposite direction. The resultant force will be, of course, the subtraction between these two forces, and its direction will be toward the biggest one. We will see. This is the first force, K, Q times Q, the test charge, Q1 times Q, over the distance square, which is 10 centimeters, 0.1, negative K, Q2, Q, over the distance, which is, I think, 5 centimeters again, but to the left. You can see them here. Okay, again, Q has a negative charge, but we already used it when we determined the direction of each force. And these are the two terms. We have them directly. I compute them. For the first term equals 10.8 to the left. This is to the left. Negative 21.6 to the right. The answer is negative 10.8. Means that it's to the direction of the biggest force. The biggest force is the second force, which is to the right, as you see. So it will be to the positive direction in this coordinate system. So it is here, if I need to write it, F total, it is not to the negative direction, it is positive 10.8 in x direction. So the resultant force will be to the right from here. Means that Q2 wins, not Q1. Sorry. This is the direction of the biggest force, because we put F1 minus F2, the resultant is to the negative direction of F1. Now, what if we used the test charge at the third point, which is C, which is to the left of our system? We have two attractive forces from Q1 on Q, from Q2 on Q, both of them to the right, as you see. If we need to find the resultant force, it's the addition between these two forces. Now let us just compute them. This distance is 10 centimeters from Q1, and it is 25 centimeters from Q2. Now directly, if you remember, we saw that here we have K, it's a common factor. We have Q, it's a common factor too. So I take K from both terms as a common factor. Also, I take Q from both terms as a common factor. This is just a math step, just to show you different ways to solve any math problem. Now, after defining this force, the rest is math actually. So we have the K magnitude, Q magnitude without using the signal now. I didn't use the sign because we know why we use the sign always, just to determine the direction. And I use the magnitude of Q1, Q2 and the distances, and the resultant force is 11.664 Newton to the right, okay, to the positive x direction, so that I can write the force as a vector equals to 11.664 in the positive x direction. Now this is in one dimension. Now I will move to solve a problem which is a smaller problem actually in two dimensions. Now I have Q1, Q2, Q3. They are located in XY plane. At the origin, I need to consider my origin at Q2 because I need to compute the resultant force from Q1 and Q3 on Q2. Now my test charge is Q2. Q1 is positive 3 microcoulombs, Q2 is positive 1 microcoulomb, Q3 is negative 2 microcoulombs. Now the force between Q2 and Q1 is repulsive force, which means it will be to the negative x direction here. If I have, this is x direction and this is y direction. What about the force between Q3 and Q2? It's attractive because this is negative. It will be to the negative y direction, as you see here. So we have two forces, one of them to the negative direction, the other is to the negative y direction. The distances between the charge, the R12 between 1 and 2 is 0.2 meters. The distance between Q3 and Q2 is 10 centimeters, which is 0.1 meter. Now we need to find each force. Let us find the first force, F12, using Coulomb law. It will be in the negative I direction or x direction, or sometimes we call it to the west, because we have, this is west, this is east, this is north, this is south. Okay, using the Coulomb law between Q1 and Q2, we know R12 from here. The resultant, the force F12 equals to 0.675 newtons to the negative x direction. The same way for the force between 3 and 2 charges, it will be by using K, Q3, Q2 over R between Q3 and Q2. It will be 1.8, which is bigger than this one, to the negative y direction. But now we have a different way to add these vectors together. We have them like this. We have F1, 2 to the west, yes, which is to the negative x direction. We have F3, 2 to the negative y direction or j direction. The length of each force of those is proportional to its magnitude. If you look here at the first force is 0.675. This one is 3 times much than this one. So the length of F32 is 3 times almost to the first force. How we can do that? It is simply by taking the second force from tail to the head. So we consider this length as F32, or we can use it F32 plus F21. And this is the angle, this is the resultant force. Now between the x direction and the y direction, this angle is 90. So we have a right triangle here. If we consider this F21, and this is the angle of the resultant force from the negative y direction. And the resultant force is F. We can consider it as F total. What is the length of this force or this vector? It's simply, we can use the Pythagorean law to find that, which is F32 squared, the length of it, plus the length of F12 squared, which is equals 1.92 newtons. So this is 1.92. What's the direction? I can use the identities, sine, cosine, or tan. I will use tan. Now the tan theta is this side divided over this side, which is F21 over F32. I'm talking about the lengths. I don't need tan theta. Actually, I need theta. Okay, it's tan inverse. Or from the calculator, you can see it as A tan. Some calculators, you can see it tan inverse. Some calculators, or it's A tan if you use your PC. So theta is tan inverse to the same magnitude, the same forces, F21 over F32. So theta, it is equal to 0.359 radian degree, or radian. It's not in degree. I don't need to use this sign of degree. Okay, which is equal to 20.56 degrees. So I have it in radian and in degrees. If I need to write F as a vector in I direction or in J direction, it is simply I just put the magnitude of each component as I found them. This is the first force, this is the second force, X component, the Y component in with negatives. And this direction angle, it's from what? From the negative Y hat or negative J hat. These are two simple examples in 1 and 2 dimensions. We can solve them or solve more examples in more directions, in 3 directions, but we will see that in the next lecture. Maybe we will solve more examples. Thank you.